So we're going to spend just a little bit of time talking about image reconstruction. Here's my objectives. I want to talk about the operations of algorithms for data analysis and creation, differentiate between raw and image data, and then we'll talk about Fourier transformations and data interpolation. I'll try to demonstrate that with some apps that I have. We'll talk about software filtering so that we can differentiate between filtered back projection and iterative reconstruction, which is the article that I gave you. Hopefully we all had a chance to look at that article. And then we'll compare and contrast scan field of view, display field of view, and illustrate the use of RAS coordinates. So the big takeaway for us today is to make sure that we can distinguish between the problems with the scan field of view and display field of view and potential problems that can come with not having those set up right, and then be able to use these RAS coordinates. So the terminology that she first introduced is that algorithms are a finite set of unambiguous steps that are performed in a prescribed sequence to solve a problem, right? Now that sounds a little nerdy and stuff. If you want, there's actually a really good Netflix documentary from the BBC called Algorithms that's really fun and interesting, and they talk about algorithms, for example, that are used for locating kidney transplant donors with a recipient so that they can do like three-way swaps for kidneys and stuff like that. That's all an algorithm. But the algorithms that we use in CT are going to be used to reconstruct the images. The Fourier transformation we use to decompose an image into its component parts, and then we're going to back project it. Okay? And we'll talk about what that looks like here in just a minute. I know that sounds kind of heady. The final thing is interpolation. And so this is a way of mathematically estimating a value using functions. Okay? And she does not really talk in a lot of detail about it, so I want to sketch this out real quick. One of the things that we do is we talk a lot about 360 interpolation versus 180 interpolation. In CT, those are kind of the two options that we might use. And for the X-ray tech folks in the room, this will look kind of familiar. This is a sine wave, right? And so it's very similar to rectification, to power rectification. This interpolation process, we are now going to do that rectification with data. We're going to do that with data. So we've got like an imaginary line that separates the waveforms, the sinusoidal waveform. And if you think about it, what 360-degree interpolation does is it takes a point right here, so this would be 360-degree interpolation, and then it goes 360 degrees along this sine wave, which from the point of view of a sine wave looks like it goes to here, right? And then it is going to reconstruct all the data from here back. So it has a larger sample. There is more likelihood of it having some kind of other data that might be mixed up in there, right? Like we talked earlier about, like we had that weird looking frog thing, and it was between two slices, and it thought that the frog was halfway through the slices or whatever. It can cause those kinds of errors, right? Those misregistration type errors. Versus if we're talking about 180-degree interpolation, we've got the sine wave, right? And we've got our data sample, and now we're just going to interpolate to there. We're just going to do half of the sine wave. So we're going to call that 180-degree interpolation. This, as a rule of thumb, is going to be more accurate because the sampling points are less further apart. They're closer together. So 180 degrees, smaller degree angle, the points are closer together. The points are close together, we're going to have more accurate signal. So, what are we talking about in terms of the data that we're accessing? So, we call it raw data when it has not yet been reconstructed. Okay? And the raw data is going to take a lot more computer storage space. So when you're looking at CT scan data, the raw data has everything. It has the signal, it has the noise, it has everything. It is a large chunk of data. So the image data then has been refined. It's been carved down to just what we need to make diagnoses. So it is a smaller data set, and it's been processed down into pixels so that we can understand it. And the pixels are important because, number one, we can spatially represent them. So we can say that they're somewhere in this area, right? So we can map them out. And then number two, they have some attenuation value. Each pixel has some attenuation value, right? So the two big things here are that they have a spatial resolution, and then they also have some kind of attenuation value. We typically talk about that as a Hounsfield unit. There are terms that we might use interchangeably with Hounsfield units. Sometimes those are referred to as CT numbers, right? So CT numbers, Hounsfield units, same difference. But each one of those is represented in the matrices of pixels. And that's what we use to form our image data. When we think about Fourier transformations, this can get really confusing really fast for people, right? So I want to show you two things real quick. So this reconstruction process is important in that we have this DOS that we've talked about that's going to read each arriving array and measure how much of the beam is attenuated, and this is what we call a ray sum. So all of the ray sums make up a view, and then the views are used to make an image. And I've just condensed down a lot of the information that is here on the bottom of page 25 to 26. If you see there's a key terms box, box 37 on page 26, it gives you definitions for each one of these. So you'll notice, like in this lecture so far, noticeably absent is I'm not interested if we're talking about LCD monitors or cathode ray tubes or any of that junk. Like that's kind of 1990s stuff. But this stuff's not going away. Like the ray sums and the views and how that's used to construct an image, these are terms that we'll continue to use and talk about. They'll haunt us in our dreams. Okay? So that box is really important. I would star that. And other things that are worth kind of looking at is, again, the key term box 3.2 about interpolation, just defining that, defining raw data. And then talking about raw data, at the bottom of page 25, this left column, the same raw data may be used later to generate a new image. So the reason we hold on to that raw data set, even though it's so big, is as long as I have that raw data set, I can make all sorts of different kinds of pictures out of it. I can reconstruct into 3D, I can reconstruct into a bone window or a soft tissue window or a lung window. I can change all sorts of things with it as long as I have that raw data. If I no longer have the raw data, I can't do that. Okay? So that's a significant part of our job that's there at the bottom of page 25. So continuing along on page 26, we're going to make an attenuation profile for each view, and that's where we're going to get all this pixel data, the Hounsfield units and CT numbers or whatever we want to call it. And then we're going to back project that onto a matrix. So now we're going to back project it out into image space so that we can say spatially this is where this stuff is going on. The computer doesn't care about any of that. The computer thinks about it in K-space, but we need to back project that into image space so that we can look at it and understand what the heck that is. Right? I look at K-space, I can't see anything. It just looks like a bunch of numbers. So perhaps one of the most important things about this is on page 26. There's a significant drawback with back projecting things onto the matrix. It will produce streak artifacts. So this process of back projecting, we will not be able to get rid of noise without increasing patient dose. Right? Filtered back projection directly ties our signal to our noise. So to increase my signal, I'll have to increase my patient dose. And so that's one of the reasons I wanted to share that article with you, because of that. This process, just below that on the page, this process of applying a filter function to an attenuation process is called convolution. There's a $5 word worth memorizing. So I would highlight that, and then it talks about how the Fourier theory is used to reduce noise. Statistically, we can use it to reduce noise. And I kind of showed you a little bit how we manipulate K-space to edge enhance or things like that. Same process, that's how we can reduce noise. With this, we might use different things to talk about this filter, right? So when I'm talking about this kind of filter function, whenever I'm talking about this type of filtering in a test, I will very specifically say filter functions. I'm not talking about aluminum pieces that are there to harden the beam. That's a filter, right, that we place on the beam to increase the average energy of the X-ray beam. I'm talking about filter functions, things that are applied to the data to change the data a little bit. Another term that we might use for it, we might just add convolution to it, so it might be called convolution filter. We might call it a kernel. I will use the word kernel and filter interchangeably. Kernel and filter function, I will use these words interchangeably. That's okay, I'm not trying to freak you out. But kerneling is a very specific kind of filter, right? That essentially looks at the matrix. It has its own matrix, and so it's like a smaller matrix that then looks at the larger image matrix and moves things around based on the numbers in the smaller matrix. We'll call that kerneling. In some manufacturers, I can't remember who uses it. I know it's not GE or Siemens, but maybe Toshiba or Hitachi or one of those manufacturers uses kernel. So there's a bunch of different kinds of filters available. We have ones that will smooth the data. They can reduce artifacts, like there's metal reducing artifact filters and filter functions. And again, they're just different types of algorithms. And this is just kind of reiterating what I was just saying, this slide here. This can all be found on page 26 in our textbook. I would say it's a really, really critical page in our textbook to make sure that we understand how the image data is sampled and then how it's filtered in order to produce an image. And she gives us all the little working parts to that pretty quickly. So let's talk a little bit about adaptive statistic iterative reconstruction, or I might just call it iterative reconstruction, or to further confuse the X-ray students, I might just call it IR, right? Because IR for y'all means something different, but IR from a CT tech point of view means iterative reconstruction. There's a bunch of different ways that we, like the article talks about, it's very manufacturer dependent. These things are developed in a black box. No one really knows exactly how they are made or produced or what exactly they're doing. So we've had to rely on a lot of health physics to tell us this is exactly what it's doing. I know that there's some interest in like CT 3D printing. So taking, like, for example, a CT scan of the heart, now making a 3D print of the heart, or a CT scan of the skull, 3D printing that data, and then doing surgery from it. But one of the other things that we're using 3D printing for is 3D printing of phantoms or models that allow us to test iterative reconstruction things. So I talked to some physicists about that and how that works. This is basically a newer method of image reconstruction. And the downfall of filter back projection, I said, was twofold. Number one, it creates streak artifacts, right? It's not able to get rid of all the noise. And number two, it is directly tied to patient dose. So if I want to increase my image quality, I have to increase patient dose using filter back projection. Iterative reconstruction untethers both of those, right? And I'm not trying to freak anyone out, but the way it does it is basically it models the CT computer system, right? So if you can imagine that picture of K-space, right? But now take a picture of the picture. That's what iterative reconstruction does. It understands that it's trying to understand the fact that I'm messing with K-space on an iPad, right? Filter back projection, I'm just messing with K-space. Iterative reconstruction, I'm messing with K-space on an iPad. The computer understands that I'm manipulating things with a computer. It's a really interesting thing to think about. And it is able then to think about noise at a higher level. It's able to think about noise in terms of geometry and things like that. When I'm talking about geometry, that article I talk about beam geometry. So it's able to account for focal spot size, or it's able to account for where the detector was as it was swinging around the patient. And as it's thinking about that, it's able to say, hey, things got really noisy right there. I'm going to get rid of that. And I'm going to go to this detector slice here where it wasn't so noisy. That's the big takeaway there. But the important thing for y'all is basically iterative reconstruction allows us to improve image quality while reducing patient dose. So compare and contrast, filtered back projection, improve image quality, increase patient dose. Iterative reconstruction, improve image quality, reduce patient dose. Okay? We'll be coming back to it in the summer because it's not all great. There's some problems with it, but we should go ahead and introduce that term now. The scan field of view. I just kind of demonstrated this earlier using that web page, but it is determined by the degree of the fan beam angulation. And so if you think about it, if I just draw like a person's body here, like say this is the person's body, the fan beam there is only going to be able to sample that smaller part because of its angulation. Versus here, it's able to sample the entire patient's body. So the scan field of view is directly tied to the degree of fan beam angulation, right? And the important thing for us as technologists here is if I didn't sample this, guess what? I can't get that. I can't go back and make that, right? If it was not in scan field of view, it's not ever going to be in the raw data. It's gone. Like as far as the CT computer goes, that stuff doesn't exist. So if I want to get that stuff, I'm going to have to rescan the patient, period. I cannot create that image data. So anything outside of that scan field of view is not going to be imaged. And it's important to make sure that we choose a scan field of view that approximates the size of whatever we're scanning. Versus display field of view. Display field of view is just what we've chosen to display. So we have this chunk of raw image data, and now we're going to reconstruct to this size. She mentions that it works similar to like the zoom on a camera. So if, for example, I do not have data, I cannot see an image or parts of an image on a display field of view, I can increase that display field of view out to whatever the scan field of view is and display it, right? And she gets into kind of the nitty-gritty with that here on page 28 and asks, one thing that I would look at is clinical application box 3.1. These boxes are actually pretty good because she asks questions that directly tie to how this would work in the clinic. And I will probably ask some questions based on this box in particular, clinical application box 3-1, page 29. I'll give us some example problems of how to think through that so that we make sure that we get all the anatomy that we need and nothing more than that, but nothing less. Okay. So the big takeaway here is understanding these RAS coordinates, which she talks about on page 30. And I've put a bunch of stars along image center because if you wind up doing any kind of radiation therapy planning, like treatment planning, if you wind up doing interventional stuff with CT, if you wind up fusing PET and CT images, understanding this is going to be essential, right? So this affects all of us, this very, very simple understanding of RAS coordinates. That when we set an image center, when we zero that patient out, we've determined where isocenter is going to be located in their anatomy. And we can now move from isocenter along the axis of the CT images and make measurements. We can make determinations of size, distances, all of those kinds of things can be made from that image center. And so we'll see a little bit more what that looks like here with some activities. But I want us to, like I mentioned last week, go ahead and start being able to orient ourselves within the images and navigate through these in kind of a three-dimensional way. So here's an example of what that looks like. And they have traditional XY coordinates, just like what we would use in like 8th grade algebra or something. And so we have this, Cartesian plane, right? A y-axis and an x-axis. And we're going to use those coordinates to navigate around on these images and make points, right? Now, I've said that, so, and I would express that as like x, y, whatever it is, right? In addition to that, this is a two-dimensional plane, right? Like it has an x-axis and a y-axis. With CT, we also have this z-axis here, right? And so in addition to saying it's x, y, z, I can now say this point is x, y, z, right? So I would say that's three-dimensional then. And that's why I'm challenging us to think about it three-dimensionally. When we start to add contrast to it, we will think about it in 4 dimensions, right? Because this point now is being influenced not just by its spatial location, but also by the profusion of contrast over time, right? So time would be that 4th dimension in this system. But for right now, I just want us to focus on image center, understanding left, right, ant, post, sup, inf, and navigating through these images. So here's an example from the textbook. This is page 30 again. She's got where she's navigated using this RAS coordinate system to find, it looks like, the north pole of the patient's right kidney here. And she's said that that is this point here. We could also locate it along the z-axis some way.